Okay, so now we're on to bigger and better things. And this next equation is called the F test, also known in quality control as the FU test. Why do they call it that for? Well, this is a way that the departments can compare people to each other. Ooh, now we're talking serious beans here because I've got one employee that's in a lab doing a test, and I've got another employee in the lab doing the same test, and I'm told by my supervisor that we're going to have to cut a job. Too much payouts. So I've got to figure out who to let go. And the F test is one of those tests that can help us determine which analyst I need to get rid of. Yeah. So what is this F test all about? Well, the F test compares what we call standard deviations. Well, we know what standard deviations are. Standard deviations, that's how close my numbers are to each other. So think about the dartboard example. If I'm throwing my darts all in one location, then I have a really tight standard deviation, meaning really, really low. Low standard deviation is good. That's what I want here. The higher the standard deviation, the more varied my answers are. So I've got two employees. One person throws his darts at the wall, and they all are grouped close together. My second employee throws their darts at the wall, and they're grouped close together, and I've got to figure out who's closer because that's what this is all about, right? It's about precision and it's about accuracy. And I want my lab to have really good precision and really good accuracy. So this is a way that I can compare those two standard deviations or those two people with each other. So in the PowerPoint presentation, this is the slide that we're on, and this gives you the equation that we need in order to calculate the F test. So if you notice, it's a pretty straightforward, simple calculation. The only thing that I have to do to calculate the F is to take my standard deviation of one of them and square it, and take the standard deviation of the other one and square it, and take those two and divide them. That's all that I have to do to calculate the F value. Now, there's a caveat here. There's something that has to happen in every single case, and that is always put your larger standard deviation on top. That is the recommended order there, right? So this number should always be larger than 1. If your F is lower than 1, then you've got those flipped around and you need to reverse them and you need to try the equation again. But the F should always be greater than 1. All right, so once I do that, I then compare my calculated F to a table. And I'll show you what that table is here in a minute. Okay, so let's take a look at an example. So let's say that in a laboratory, I have two people that I want to compare. Here is my first person, number 1, and here is my second person, number 2. And I give them an assignment, and they analyze this sample for me, and they give me the results back, and I go through and I calculate the standard deviation for them. So this first person did 8 measurements or replicates on the same sample, and their standard deviation was a 0.00138. And then the second person has a standard deviation of a 0.000143. And they only measured it 7 times. So is there a difference between these two people's precision or how close their darts are together on the dartboard? And the answer, it's either yes or no. Are they different or are they the same? Well, I take a look at the two standard deviations, and I see that number 1 is a 0.001 and number 2 is a 0.0001. Okay, well, to me, that could be different. right? Just by looking at the face values of the numbers, they could be different. But statistically, I want to prove it. Mathematically, I want to prove, are they different? Are they the same? If they're different, then maybe I can get rid of one or the other. If they're the same, well, my analysts are really reporting the same type of data to me, so I would want to compare maybe two other people instead. All right, so the way that we determine that is that we use the F-test if I just want to compare standard deviations, and I take my larger standard deviation. So my larger standard deviations here, number 1, so 0.00138, and I want to square that number, and then I'm going to divide it by the standard deviation of the other one. So that's 0.000143, and I'm going to square that number. All right, so again, I'm going to do this in baby steps. It's okay. 0.00138, and I want to square it. So that gets me point, and I see all of these zeros. 1, 2, 3, 4, 5 zeros there. 190. 1, 2, 3, 4, 5, 190. And then I'm going to divide that by 0.000143, and I'm going to square that number, and I get a lot of leading zeros there as well. I have 1, 2, 3, 4, 5, 6, 7 of them, 204. 1, 2, 3, 4, 5, 6, 7, 204. All right, and then I finish calculating my F. So 0.000190 divided by 0.1234567 and I hit enter, and I get a 93.1. All right, so that is my F calc. All right, well, just like before, I'm going to compare my F calc to my F table. All right, so my F calc is 93.1, and I want to compare that to my F table number. That is the standard that I compare that by. All right, so this is the F table. Again, this is in that handout that you have in the PowerPoint or in the Blackboard lecture module. And on page, who knows at this point of the document, you will find this section titled 4.4, Comparison of Standard Deviations with the F-test. It gives you the equation for the F-test here, and then it gives you this table down here at the very bottom. Notice that S sub 1 is up at the top. So degrees of freedom for S sub 1. That is the degrees of freedom that I want to pull from. All right, so degrees of freedom, not the number of measurements. So S sub 1, well, this is the number I used on top. That number was from here. That was 8 measurements. So 7 degrees of freedom. The other one would be 6 degrees of freedom. So 7 degrees of freedom is going to be here. 6 degrees of freedom for S sub 2 is going to be there. And I cross-reference them. Right? I see where they intersect here at the table. And right there is where they do that. 7 and 6 cross over at 4.21. So that is my table, my F table value, 4.21. Okay, so 4.21. My F calculated is greater than my F table. So that means that these two analysts are different, and that means one is reporting better data than the other. And just by looking at the two standard deviations, I would kind of know that already, because this person's standard deviation is a 0.0001 and this person is a 0.001. So this person has a much lower standard deviation, which is a much better data set. And if I had to get rid of one of these analysts, it would be number 1, because they have the higher standard deviation. If my F calculated was less than the F table, then they would be the same. And I really couldn't say with justification this analyst is providing better standard deviation than this analyst or vice versa. All right, so that's the story with the F-test. That's all there is to it. You take the standard deviations, you plug them into that equation, you square them and divide them. Then you compare that to the F-table, and you saw how easy, hopefully, that F-table was to read. So again, that's in that PDF document that's been uploaded. That's how you'll read the table, and of course you'll have that table whenever you need it. So there's the F-test. So the next video, we've got one more equation to talk about, and that is the Q test.